Welcome to our next section in our journey into linear algebra. And as I mentioned before, this is a fairly chatty lot of notes and examples. So we're going to look in this section at the Cayley-Hamilton theorem, and I'm going to begin with just a 2 by 2 matrix. And we're going to show that if this 2 by 2 matrix, which is 2, 1, 3, minus 1, satisfies this particular little identity here, that if you square this matrix, you get the same as what you started with, plus 5 times the identity. And then I'm going to show you how we can then use that to bootstrap and calculate a to the fourth without actually multiplying this by itself 4 times. So here's the worked solution to this. So here's our matrix A, which is 2, 1, 3, minus 1, and I'm just going to check the identity we were given. So I'll work out A squared the long way, so you just got to multiply these out. You should be very familiar with matrix multiplication as to how to get these entries here. So we get 4 plus 3 is 7, 6 minus 3 is 3, and so on. And I checked the other side of the identity, which was A plus 5i, so that's A plus, that's 5 times the identity, and we add those together, and lo and behold, we get the same expression here, which is just equal to our A squared. So that establishes this little identity that A squared is A plus 5i. Now to get A to the fourth, well, we can get that by just squaring both sides, so I'm going to square both sides. Now I and the identity matrix commutes with everything, so AI is the same as IA. You've got to be very careful when you square out these binomials with matrices, because in general they're not going to commute the terms in here, but the identity does. So I get 5AI plus 5IA, which just gives me 10A, and then I get 25I squared, but if you square the identity, you just get the identity again. Now I can now bootstrap this. I can now use the identity for A squared. I can replace that in here and write that as A plus 5i plus 10A plus 25i, and simplify gives me 11A plus 30i. And if you wanted to work that out explicitly, well, you just multiply A times 11 and add on 30 times I, and that gives me this matrix here, which we got without having to multiply A by itself 4 times. Indeed, we could use this method to work out, I'm sure you can see that you could work out, it takes a bit of time to do, but you could work out any power at the moment of A by using this particular method. So this example invites a number of different questions. Firstly, given a matrix A, can we find some polynomial equation which A satisfies? So in the above example, the matrix A satisfies this quadratic identity here, x squared minus x minus 5 is 0, this quadratic equation I should say. What we do is we simply replace 5 with 5i and replace x with a, so we get a squared minus a minus 5i is 0. So given a matrix, can we find such a polynomial? Secondly, if we can find such a polynomial, how do we know that there's no polynomial of smaller degree which A also satisfies? That is the polynomial minimal? And we're going to see sometimes it is, sometimes it's not. And finally, given a polynomial, can we go backwards? Can we find a matrix which satisfies it? So that's what we're going to be looking at in this section here. So firstly, I want to come back to this definition you will have had from before in your study of linear algebra, which is the characteristic polynomial, because the answer to all of the questions we've just been looking at was all connected back with eigenvalues and eigenvectors again. So from the theory of eigenvalues, we had the following definition, that the characteristic polynomial of a square matrix A, it's defined to be char poly of A. Now, various books do different things here. The correct, in inverted commas, definition is det lambda I minus A. Generally, when you're working out the characteristic polynomial to get the eigenvalues, you look at the determinant of A minus lambda I. So this here is simply plus or minus that determinant, where you choose the sign to make the polynomial monic. That is, you want the leading coefficient to be plus 1. So if you take this without the plus or minus, the leading coefficient sometimes will be plus lambda to the n and sometimes minus lambda to the n, depending on the parity of n, whereas this one is always going to be lambda to the n in general. So in practice, I generally work out this thing, and then if I'm out by a minus sign, I just whack a minus sign in front of it to get the characteristic polynomial. But by definition, the characteristic polynomial should be monic. So if A is an n by n matrix, then the char poly of A is a monic polynomial of degree n. Now, just to tantalize you here, note that in the above example, when we took this matrix, its characteristic polynomial, which I leave you to check, turned out to be lambda squared minus lambda minus 5, and that was precisely the polynomial we used to get our identity. So we had a squared is a plus 5i. So it's going to be, it looks like what we're headed towards is the characteristic polynomial is going to give us the polynomial that the matrix satisfies. And that is our rather big theorem for this section. So just as an example, we're going to find the characteristic polynomial for this 3 by 3 matrix. As you'd expect, it will be a cubic. So here's the worked example for this. So what I've done again is there's the matrix B, and I'm going to work out, I'm going to use B minus lambda I, and then I'm going to just change the sign to get the characteristic polynomial. This is the most natural thing to do when you're working out the eigenvalues. So I simply set the determinant of this thing here. So this determinant, I subtract lambda off the main diagonal, and you've got to expand this out, which I haven't done all the arithmetic here, but you will have this one, cross out the row and column. It'll be this times this minus 0. And then minus 1, cross out the row and column. I'm going to have that times that minus this times this. And then minus 2, cross out the row and column. You get this times this minus this times this. Lots of signs to worry about. You expand it all out, simplify, and I think you end up with this polynomial here, minus lambda cubed plus lambda squared plus 10 lambda plus 17. Now this is not monic. So to get the characteristic polynomial, I'm just going to multiply this through by minus 1, and that will give me the characteristic polynomial. And that's all we do to calculate that. Now we can we want to reverse the question a little bit now and say, well, given a polynomial f of lambda, can we find a square matrix A whose characteristic is f of lambda? And this is going to be really done by pattern matching here. So starting off with a quadratic, there's a general monic quadratic, and I'm going to write this in a special way. I'm going to write this as take a lambda out of this, so I have lambda times lambda plus a1, and then I'm going to write the a0 as a0 times 1. And I can now think of this now as a determinant of, I want lambda times lambda plus a to give me this term, and then I want minus 1, and then a0 here. And in fact, would have been more sensible to have written plus 1 here and put the minus 1 here. Sorry, no, not more sensible to do that. I'll leave it as it was. Sorry, so it is minus 1. I write this as a0 times minus 1. Now I can then write this one now as lambda times lambda 0, and then minus 0. I'll need a minus a0 there to give me the plus a0. I'll need 1 there to give me that one, and then a minus a1 here. So it's just a little bit of sleight of hand there of taking the polynomial and rewriting it in this way to try and do some pattern matching. And this one here now, so the underlying matrix here is this one. So this is the determinant of lambda I minus this matrix. And so this is the characteristic polynomial of this matrix here. Now you can do a similar thing for the cubic. It's a little bit more fiddly, but you can do a similar thing for the cubic to try and pattern match. And so we have 0, 1, 0, 0, 0, 1. Notice that this one is E2, and this one here is E3, our standard basis vectors. And then I get minus A0, minus A1, minus A2. And if you get the characteristic polynomial of that, turns out to be this generic monic cubic. Now, again, a bit of pattern matching, and you can prove by then induction. We can now make an intelligent guess as to what we think the companion matrix is going to be for a general monic polynomial of degree n. We're going to take the matrix to be, down here will be E2, and then E3 and E4 and so on until we get down to En, our standard basis vectors. So this one here is E2, E3, this will be En here. And then we take the coefficients, we take minus the coefficients but backwards. So we start with the constant term, so minus that, and so on down to minus this one. And this matrix here is called the companion matrix, and it's not hard to show by induction that the characteristic polynomial of this matrix is just this here. So that answers the question, given a polynomial, well here's a general monic polynomial of degree n, can we find a matrix which is the characteristic, which has this as its characteristic polynomial? The answer is yes, and there it is. So if the monic polynomial f lambda is given, we can easily write down a matrix C, and that's called the companion matrix. And just as an example of that, we'll write down the companion matrix of this expression here. So here's the solution of this one here. There's our cubic. And it is the characteristic polynomial 4, so it's a 3 by 3 matrix. We put E2 here, E3 here, and we write the coefficients backwards, changing the sign. So it's minus 6 plus 4 minus 3. So it's very easy to write down the characteristic polynomial for, to write down a companion matrix once we're given a monic polynomial. Now, just coming back to our main question about finding, about seeing whether the matrix satisfies these polynomials, in this little lemma, which I will go through the proof of here, it's worth doing, it's not that difficult. Here we're going to take f to be a monic polynomial of degree n, there it is, and C is its companion matrix. And in this little lemma, we're going to show that if you replace lambda with this matrix C, and of course you replace A0 with A0I, then f of C is just the zero matrix. So f of that is just the zero matrix. That is, the companion matrix satisfies its own characteristic polynomial. So first of all, remember the way we constructed these. We take the standard basis vectors, and we saw that the first column of C is E2. So if I multiply C by E1, the first basis vector, that's going to pick out the first column of C, and the first column of C was E2. If I square this, C squared times E1 is just C times E2, and remember that if I take out the second column of C is just E3, and so on, and this of course is going to mean when we get to the end, the second last one, Cm minus 1 E1 is C times En minus 1, and that was just our last basis vector. The final column, if you multiply C to the M times E1, then in this case, so C to the n times E1, in this case, you're going to pick out the last column of C by what we saw up here, it's just C times En. That's the last column of C, which was this funny column with all the coefficients minus in this order. And you can write this as minus AN E1 minus A1 E2 up to minus AN minus 1 En. So we just hold that thought. Now, if we now substitute C into this polynomial, and we multiply, so this will give you a matrix. You now multiply by E1, that's going to pull off the first column of the matrix. Then, there's what we've done. We substitute C into the polynomial. That gives me this expression. And that's times E1. And when we expand this out, we're going to simply get Cm times E1. That's what we got up here. So that's this expression. And then we're going to get A sub n minus 1, Cm minus 1 times E1. We worked that out before. That was just E sub n. And so on. We multiply all of these by E1. We get all these expressions. But of course, this is just, these now all cancel out to give me 0 vector. So that means f of C is now an n by n matrix whose first column is all 0. Now, C and f of C commute with each other. So to pick out the second column of this matrix f of C, I just multiply this out. And E2 we can write as C times E1. These commute, so I can pull the C over here. And we've just seen that f of C times E1 is the 0 vector, and C times the 0 vector is the 0 vector. So that tells me the second column of f of C is 0, and so on all the way down. So every column of f of C is 0, and therefore this is the 0 matrix. And we'll see in the next recording that this is a special case of a more general result which is called the Cayley-Hamilton theorem.